Okay. Good evening, everyone. And welcome to this week's seminar course lecture. So our first presenter, so we'll have two exciting presentations today, both on how to accelerate parts of the LLM pipeline. And our first presenter is Lionel Nusi. He's a master's student in the second year in electrical engineering and information technology. He's interested in digital circuit design and EDA, and he's also interested in integrating new technologies and devices. The first work is called REIS, which was published in ISCA this year. So I'll leave the stage to Lionel to continue.
Okay, hello everybody. Today I'll present to you REIS, a high performance and energy efficient retrieval system within storage processing. As already mentioned, it was presented at ISCA this year. And yeah, let's get started. Okay. Tap on the screen. Nice, okay. So let's start with a quick executive summary. Okay, yeah. So the problem is that during RAG pipelines, basically the terabytes of data within a solid state drive has to be processed by a host system. And this results in a huge input-output bottleneck because, yeah, we really have to look at all of the embeddings and find out which kind of document fits best. So I'll explain RAG in a second. But yeah, the goal of this work was basically to avoid this data movement by processing inside of the storage and to speed up the search process, and yeah, without introducing new hardware modifications, because a lot of previous work has tried to do that, but they just basically rebuilt this SSD, and the goal was to kind of use the existing elements to do that. So yeah, this work developed this ISP-friendly algorithm in storage processing for this approximate nearest neighbor search, which is part of the RAG pipeline. They utilize only already existing components in the SSD. They had a new database layout as well, which allowed for less address translation and for like these efficient links between embeddings and documents. And they used some new techniques as well, like input filtering, quantization. They experimented with different quantizations and pipelining. And at the end, they showed basically 13 times more queries and 55 times more energy efficiency than a CPU. And they also compared it to other state-of-the-art ISP approaches and showed a 2.5 increase over those. And they validated on multiple data sets and different SSD configurations and yeah, different CPU metrics as well. We'll see all of this later. So let's start with some background. Super high level RAG, basically you have an LLM and you have a query, and instead of only feeding it the query, you also have this huge database of document chunks where you want to find like the K most relevant ones, like for example, 10 documents. And this is so that you can basically provide the LLM with up-to-date data without having to retrain it, because retraining takes a long time and, you know, yeah. So how does it work? In the first step, it's called the indexing step, but you basically have this embedding model, which creates these document embeddings and query embeddings from the query and the document chunks. Now, obviously, these are static, so they only get computed once. And the goal is to kind of bring documents and queries which have a similar meaning to get mapped to similar vectors, which are close to each other. Now, after you have those, usually the documents are stored externally, and then the query obviously comes to the host system. And what then needs to be done is each document embedding has to be brought over to the host system. The distance has to be calculated between them. And this has to be done for each of the document embeddings. At the end, you look at, okay, which document was basically the closest to my query, and then you pick it. But you have to keep in mind that in a professional system, there can be millions of embeddings. And each of these embeddings is not like a vector of like 5 or so, but 8,000 dimensions. So this whole process of sending stuff from the SSD over to the host system can take a long time. Now, obviously, this was a simplification. There are many different ways in how we speed up this process in modern systems, and by basically not calculating the distance exactly, or like a brute force algorithm, but by approximating it. So there are some algorithms. I'll talk about them in a second. We have the inverted file, hierarchically navigable small world, locality sensitive hashing, and different types of quantization. But before I explain this, I also want to introduce a metric, which is the recall metric. It's basically accuracy, but dependent on K. So like, let's say if we have recall at here 5, for example, then the left one would be the actual 5 most relevant chunks. And here are the chunks retrieved by the ANNS. And as you can see, only this one is wrong, and we don't have this 82 in the middle. So our recall would be 80. Now that we have this, let's look at some of the algorithms. First, the hierarchically navigable small world. This one uses basically a graph of graph data structures. And the problem with this is that we don't have like contiguous data access. So we basically don't know where we need to go next. And I think most of you can imagine that that complicates the design if you want to do all the processing inside of the storage device. And the second one is locality sensitive hashing. But for this one, they did a study on it and they found out that it loses too much recall. So the one they focused on, and which is why I explain it in more detail than the other ones, is the inverted file algorithm. And here in the first step, also you create these document embeddings. But then you create this additional indexing step where you basically group embeddings which are similar to each other into clusters. Then when a query comes, the embedding model also creates a query embedding as before. But then in the first step, instead of calculating the distance to each document embedding, you first calculate the distance to each cluster, which are a lot less. Afterwards, you only pick the closest clusters, like here. And then from all the embeddings which are left, you calculate the distance to those, filter out the K most relevant ones, find the document chunks and feed them to the LLM. And this is quicker, but not exact. Any questions? But yeah, interrupt me if you have any questions. You can just raise your hand as well. Next, I'll talk about some different quantizations. So this on the left is the actual embedding vector. Then we have integer quantization. So you basically cut the values, or no, you round the values and you size them to minus 128 and 127. And binary quantization, when I first read this, I thought this was kind of crazy. Okay, how do you just turn a float into a 1 or a 0? But keep in mind that we have like 8,000 dimensions. So this actually works, and they showed this. And the last one is kind of this product quantization. It's kind of special, but you have basically these subvectors, and you basically find the cluster IDs of those, and then you fill the vector. This is now a shorter vector with only the IDs. Yeah. But all of these quantizations, especially the last two, obviously those are really high quantizations. So what can be done as well is to introduce this re-ranking, which is that we first calculate the top 10K. So let's say if we want to find 10 documents, we find 100, 10 times K, with this really high quantization. And afterwards, after we have this 100 embeddings, we then use like maybe integer quantization to find the actual top 10. So this is kind of the trade-off. Yeah. Also a small schematic of how an SSD is built. You have also all of this is the SSD, and then here you have the controller. You have embedded processors, which do most of the work. The controller then talks to each of the chips. The chips is where the actual memory is stored. You also have some buffers for reading and writing, and some peripheral logic for small computations which are done on the flash directly, and to also like initiate the reading and writing process. And what has been noted, and you also have the DRAM up top, sorry. Yeah. The embedded processors are general processing elements, so they can do anything, but they're not optimized for speed. So they have limited performance. What is also important is you can see one flash controller talks to multiple flash chips. So this bandwidth here is actually limited, and you basically cannot have all of the flash chips sending like a bunch of data at once. And this peripheral logic is really simple. So it can only do like bitwise operations, and it's very limited in performance as well. And in storage processing, I think if you're taking the seminar, all of you know, but the goal is to basically do the computations inside the SSD. So you send the query over instead of the document embeddings, because it's only one vector. You do the processing in here, and then you send back the results only. Yeah. Now, with all of that out of the way, let me introduce to you REIS, so the work, what they did, and the motivation, for why they did that. Yeah. So here we basically have this measurement which they did. So these are two different data sets, and they basically ran the RAG pipeline, the full RAG pipeline. So not just the searching and the document retrieval, but also the generation, which you see on the right. And they basically classified, they broke down the whole execution time into different parts of the algorithm. So here you can see the biggest part is actually the dataset loading, which combines all of the movement from the SSD to the host. And you can see for a bigger data set, the fraction of execution time becomes bigger. So it's obviously a bottleneck, and it increases with dataset size. Yeah, and in our new society, we always have more data, so this is a problem. And we also see that generation is actually not the bottleneck, which I guess is kind of debatable, but because the bigger models we have, might also become a bottleneck. But we'll look at that later as well. But yeah. Then let's look at the existing methods again and why they don't solve the problem completely. One thing I didn't talk about before was batching. So you basically have multiple queries and you try to amortize this data movement. So instead of sending all the document embeddings over and then only calculating the RAG for like one query, you calculate it over all of them. But the problem with this is that the queries might come during different times and might access different types of data sets. So this doesn't work. For quantization, they also did a measurement and they saw that it doesn't really completely solve this bottleneck. It's not able to do that because we still have all of these embeddings. And if we do the re-ranking, then we need to send them over again. And also the document chunks, sending those over, those you cannot embed because the documents need to be the actual text. And then also the algorithms, they showed that it was only, or like they cited different work which showed that you could only have like a 22% speed up, and it's not scalable because there's this trade-off between, okay, how many clusters do I have? If I have very few clusters, I don't really gain a lot of performance, but if I have a lot of clusters, then I have a lot of more memory. And depending on how many clusters you have, it also affects the recall, so that's also kind of annoying. Now, they're also not the first ones to do in-storage processing for RAG, but all of the existing works, they either used this one algorithm I was talking about before, hierarchically navigable small world, which has this irregular access pattern, so they didn't want to use that one. Then none of them really focus on the document retrieval, and almost all of them had huge modifications to the hardware. So the goal was to kind of fundamentally alleviate this I/O data movement by not introducing any new hardware modifications to the storage system. So yeah, I hope now you're all motivated, and I'll explain REIS to you. So REIS stands for Retrieval in Storage. It's also REIS in German. And yeah, so they basically use existing processing elements inside the storage and flash chips to minimize the data movement and maximize parallelism. So the key techniques which they used was a new database layout. So they kind of, yeah. And they did this new database layout to basically solve the problem of address translation. So in an SSD, when you give it a logical address, the SSD or embedded processor then has to figure out, okay, where is my data actually stored? And they also have like these really convenient links between the embeddings and documents. But I'll explain the database layout in the next slide, actually. So yeah, they adapted the inverted file algorithm to efficiently run on the in-storage processing, and mapped all the computation of that algorithm to existing elements. And yeah, they used the inverted file algorithm and binary quantization with re-ranking, by the way. Yeah. So there are a bunch of challenges in making such a design. First, as I said, the embedded processors are limited in computational power. There's limited bandwidth. the computation here is limited. And if you read from a flash chip, you also need error correction. So, and this is usually done by the embedded processor. But yeah, if you read the document embeddings here and you have to send it over there, then you already have this bottleneck again. So yeah, let's first look at the database layout. So their big innovation was to basically split up the documents and the embeddings so that they're not like interleaved basically in memory, but you have one region for the embeddings and one region for the documents. And there's also this out of bound region. This is not like normally if you're a user and you store something in the SSD, you don't have access, you can't store anything here. This is managed by the embedded processors, but they repurpose this region to store the link from one embedding to a document. But this allows them to keep those two separate, have these efficient links between them. And because they're now contiguous in data, like the addresses are next to each other, because of that, they have less of this translation overhead because you basically need to do one translation for a huge chunk of embeddings. So, and what is really cool and like really important as well is how they overcame the challenge of the error correction. Because as I said, these embeddings here, when you read one of them, you need to do error correction. And so the main technique which they used is they used a different programming mode of the flash memory, of the NAND. So basically, normally when you store something in NAND, you have like this TLC, which stands for triple level cell, and you can have up to 8 values in one cell. But by basically not using this one and only using single level cells, and the whole thing is called enhanced single level cell programming, they basically can avoid this error correction because they have such a high margin for error. And they only use this TLC for the document region, because the trade-off here is kind of, okay, here you have way more, 8 times more storage density, but 3 times, yeah. And but here you need to do more error correction if you do the TLC, because here you can see these peaks are a lot closer. So if you store something as a 110, it might end up drifting to a 111 in the end. So single level cell programming, yeah. And now let's look at REIS in action now that you've seen the database layout. So you have a host system, and as I said, it sends it over to the DRAM, okay? And then the embedded processor basically sends this query embedding to all of these different flash dies, okay? So here you can kind of see the query embedding going into the buffers. And then as a next step, the flash controller initiates also the reads in the flash dies. So now you have both the embeddings and the query the document embeddings and the query embedding inside the buffers. And then in the peripheral logic, the way they basically calculate the distance is by first XORing the two and then counting the bits to get the final distance. And now why does this work? This is basically because we use binary quantization. So if we have two vectors, like let's say they are like focus just on one value. If we have 1 and a 1, then the distance between them is 0. If we have 0 and 0, the distance between them is also 0. But if we have a 1 and a 0, or a 0 and a 1, then we have a distance between them of 1. So this is what is XOR basically calculates the distance, or like the minus one vector minus the other vector. And then you count up all the bits. So this is, I guess this is the magnitude of the difference of the two embeddings. I hope that was kind of clear. Are there any questions about this? This is kind of confusing maybe, but yeah. Afterwards, the flash controller still, with the one command it sent, the flash die will accumulate all of this information. So basically the distance, the embedding vector, the document address, so the address of the document, the linked document, and the re-ranking address. So this basically stores the integer 8 quantization vector, which is needed at the end. And this whole vector gets sent back to the embedded processor, and the embedded processor then does the quick select kernel. So it basically decides, okay, is this part of my top 10K, or top 10K, 10 times K embeddings? And if it is, it will basically store it inside of its own local DRAM. And at the end of everything, the embedded processor will also do the re-ranking, look at the document addresses, read the document chunks, and send them to the host system as well. Yeah, this is the main thing. So if you have any questions on how that works, that's now. And yeah, what's important again is they actually do this processing inside the flash drives as well, which saves a lot of computation because the embedded processor does not have to do that. And they basically use this XOR and this fail bit counter, which are both already existing elements inside the flash die to compute the distance. So that is the kind of impressive part. They didn't introduce this new logic out of the blue, but these elements already exist inside the peripheral logic. Yeah. Yeah, another thing they introduced was input filtering. So they basically set a threshold. They don't send back every single embedding, but they found through tests that you can basically set a threshold. So on the bottom, I have a threshold of 100. And you can see all of these embeddings have like 3,100 and 1,029. So obviously this 3,000 is never going to be one of the top 10 or top K embeddings. So we don't even bother the embedded processor with it. And they show that basically with this technique, they can basically also reduce the processing power needed by the embedded processors because it receives a lot less embeddings. So now only one of the embedded processors is needed, and all of the other ones can be used for like a normal normal SSD work. And it reduces the channel bandwidth. And I was supposed to say that in the slide. Yeah, only one processor is needed to run the entire REIS kernel, and the other processors are available for normal SSD operation. And they also use pipelining. So while the flash dies are computing, the embedded processors are doing the re-ranking, the quick select kernel. Yeah. Now, let's look at the results and the methodology they used to kind of evaluate their system. They had a CPU real, which they called. So these are actual measurements. So CPU-based system running the inverted file algorithm like normal. And then they also had one kind of CPU configuration where they ignored all of the data movement from the host to the system and just cut that out of the entire latency. ND search is another one of those ISP in storage processing approaches, also like a state of the art. And this is what they also compared against. And for them, they used REIS SSD1 and SSD2. One is more cost oriented and the other is more performance oriented. And here are like more details. So you can see 8 channels instead of 16 channels and more bandwidth. Yeah. The data sets, they use a bunch of data sets. So all of these ones in increasing order. And then when I compared it to ND search, they used the same data sets as them, to be fair. And they also did 2 approaches. One is like the brute force exact algorithm, and the other one is the inverted file algorithm. So both of these, they can implement both of these with their REIS system. Yeah. Yeah, let's look at the results. First, performance. And here we showed a 13 times increase on average for queries per second and a 112 maximum increase. So on the bottom, this is kind of maybe a lot, but you basically have the normalized queries per second, QPS, and this is compared to the CPU. So the higher the axis, the higher the speed up compared to the CPU. You have different data sets and you have different algorithms. So here's the brute force, and then you have the inverted file algorithm, which is this approximation with different levels of recall. So this is basically different amounts of clusters. And and the green and the blue one are both REIS, and the purple one is the CPU without this IO overhead. And it's really cool because even if you completely ignore the IO overhead of the CPU, REIS is still faster on average 1.8 times and up to 5.3 times. And that is because of the massive parallelism, because not just one flash die is computing the distance, but all of like everywhere where there are embeddings. Yeah. And you can kind of see for bigger data sets, the improvement gets a lot better. So here you have this 112 times increase. But yeah, and for higher recall as well, which two metrics which we both like. And yeah, for these small data set, you can see the no I/O of the CPU is still faster, but quickly the REIS becomes faster. Yeah. Now let's also look at end-to-end performance analysis, which I guess is a bit more what was also important. So you can kind of see that here we have REIS. These are the fractions of the execution time. And here you have the CPU using binary quantization, BQ. And you can kind of see that for REIS, the bottleneck is now the generation. So here you have like a 92% for the latency contribution for the generation for both of them. Whereas the CPU basically here has like 73. Okay, here has 28. This is a smaller data set, so here the generation is not a bottleneck yet, but here it then definitely is. You can kind of see the generation is not the bottleneck, so it's 28%, but the data set loading. So we basically eliminated this data set loading bottleneck. So it's not good that the generation is a bottleneck. Maybe I worded this wrong, but it's good that we don't have a data set loading bottleneck anymore. Because now we don't send the document embeddings to the CPU anymore. And yeah, it shows like an average 1.25 and up to 3.24 whole system speed up. Now energy efficiency, same graph as before, but now queries per second per watt. And here we have an even more impressive numbers. So 55 times more on average and 112 more maximum, more energy efficiency. But this is only for the actual search process and the retrieval part. Yeah. So comparison to any search, this is the other ISP approach. And here we kind of see that we also have an average 1.7 increase up to 2.6. And the hypothesis of that is because they have this new better data placement, and they don't use this algorithm where they have to do all of these random accesses. They don't use these graph of graphs. Conclusion, RAG pipeline are bottlenecked by I/O data movement from the SSD to host, but RAG, because it does all this whole algorithm inside the storage device, and they have this new database layout which allows them to do that, and they use kind of the binary quantization adapted inverted file algorithm, and they only used existing processing elements. And this resulted in a 13 times speed up and 55 times more energy efficiency over a CPU. And even over other ISP approaches, they showed us 2.5 speed up and only use processing elements already found in the SSD. Yeah, any questions up until here before I go into strengths and weaknesses? Strengths. First, really smart use of the existing processing elements to compute the k-nearest neighbors. So to even allow them to do that, they had to use, okay, let's use binary quantization so that we can calculate the distance with this XOR and stuff which already exists on the CPU, on the SSD. And I thought that was really good. Instead of always thinking, okay, what do I need? Let's add it. They thought, okay, what do I already have? They did a thorough analysis of different algorithm approximations. I didn't talk that much about them, but they had a thorough study. A good database layout, and which is well adapted to in storage processing to avoid this address translation, and as well the single level cell and triple level cell thing, which allowed them to avoid the error correction. Yeah, to avoid error correction by the embedded processors, they found the single level cell thing, and they introduced new additional techniques like the distance filtering and pipelining. And they did a successful end-to-end implementation. So I think all of this are good strengths. Let's talk about the weaknesses. And the first thing is, does their approach really speed up retrieval of the document chunks, however? So if you can remember in the beginning, one of the reasons of their motivation was, okay, other ISP approaches, they don't speed up this retrieval of the document chunks, but only the sending over the embeddings. And they also claimed that a CPU, the reason why we can't just rely on quantization and stuff is because of these document chunks as well. So they basically mentioned this a lot in their paper, but there was no real argumentation for why their approach also avoids the data movement of the document chunks. I mean, at the end of their whole pipeline, they still have to get the document chunks, read them from the SSD and send them over. And this is not a problem. Like, I don't think there's a real way to like kind of circumvent this, but they wrote a lot about it in their kind of motivation. So I thought it was kind of weird for them to claim that the other ISP approaches were bad because they didn't speed up the process, but their approach also only sped up the search process. And there's another thing I kind of found. This is their design of their temporal top list. So this is basically every time one of the flash dice sends something back to the embedding to the embedded processors, they send back one of these vectors. And like, maybe does any one of you know if any of these entries are really useful, or if we can optimize this design? And think that the embedded processors basically use these entries to select which document should get sent back to the host in the end. Does anybody know or like have any ideas? No, okay. No, okay. I'll say I think the embeddings, like, they also send back the embeddings from the flash die to the embedded processors. But the embeddings are not really used by the embedded processors anymore. They already have the distance between them, and they can do the whole re-ranking with the distances alone. They don't need the embeddings anymore. And by also sending back these embeddings, which are really big, you kind of waste a lot of bandwidth. And obviously they kind of solve this problem with the input filtering and stuff, but I think this is also something they could have done. And another thing I also kind of thought about is their data layer really ISP specific in search processing. And I thought to myself, no, okay, you can also have the same database layout in a CPU, which they didn't try and use, because every time they basically wanted to send something to the CPU, they had to send back the whole, like both the embedding and the document chunk at the same time. And I found that also real systems actually do partitions between the embeddings and the document chunks here. And so at the end, I thought, okay, because they didn't compare their implementation to a CPU, which also used the same database layout, I thought this was kind of a weakness, because now we don't know how much of the speed up comes from what, because maybe a CPU with this database layout would be enough to kind of speed up the process. And like two other weaknesses were it's only really tailored to racks. So future algorithm changes don't really work, and it only works if you do binary quantization, because they rely on this XOR. And they do require some hardware modifications, like a lot less than the others, because no new processing elements, but they do need to introduce new instruction sets to the flash dies and change the firmware of the embedded processors. So, but yeah. And they compared basically the simulated SSDs to an actual measured CPU, which I thought was kind of like maybe an unfair comparison for their CPU numbers. So let's get to the discussion. I don't know how much time I have, but yeah. Do you have any ideas of where else such a system could be useful? So now they have this REIS in storage processing to have kind of this vector similarity search. Yeah. Okay. Yeah.
Hello. Yeah. Probably like similar image systems or recommender systems or something similar could be very useful.
Perfect. Yeah, recommendation systems and image things. That's also the same idea I had. Also like DNA sequence matching and stuff. I don't know if that's maybe too far-fetched, but also there the bottleneck is comparing DNA sequences with a bunch of huge databases of that. So yeah, I think that's a good answer. Yeah. Then I also thought, okay, how, maybe first of all, do you think their system is too specific, or do you think it's okay? And if not, how can we kind of make their system less specific to only RAG and kind of allow it to be used by these other applications as well? Or yeah. Yeah.
I'm also presenting next, so I have a,
Okay.
I have good context on that. I'm guessing it's not very RAG specific because we're doing document retrievals and then we're passing it into the LLM at the end. So if we just remove the LLM part, we still have a really good system for retrieving nearest neighbors, right? That's what I think.
Okay, actually, yeah, that is a good argument. Yeah, in my head, I thought it was too RAG specific, or I guess too vector similarity search specific. But yeah, I mean, obviously you can use it for these other things. In my mind, I was just, okay, we have this SSD, and now we add like these 4 specific instructions just for vector similarity search, which kind of makes so I guess not RAG specific, but I guess vector similarity search specific. But yeah, I like it. But also like with but I guess the RAG specific part would be more like the different metrics, because right now, okay, we showed, okay, with binary quantization and stuff, it works well with RAGs, with LLMs and stuff. But because it's so tailored to that, we kind of don't have the, if we do this do this image retrieval stuff, for example, we don't know if binary quantization works for that. We don't know if like future algorithm changes, like let's say you do need like the clusters, or you need a bit more of metadata and stuff. Yeah. And I think more research into like just allowing the SSD to be programmed in general, and like maybe having the reconfigurable hardware, because I guess I didn't really present the programming mode of them, but the programming mode, kind of had like this one additional instruction. And I thought, yeah, if you allow these things to kind of reprogram, you have more aggression. But yeah, I mean, I agree with you as well. Then the last I think the last one is to how to accommodate continuously updating datasets, because now they've kind of shown the system which really works well for databases that have specific document chunks and embeddings, and they're fixed for a lifetime. But what if we have systems where the database continuously changes? What the paper kind of suggested is that REIS periodically creates new databases to store the new information. So like once an hour, we get new information, they create a new database for that. Each database has a time step, and they treat them kind of individually. And then when a new query comes, they basically only use the newest database. But I mean, I just said it, I guess. What are the problems with this proposal? I think that this loses most of the old information, because they only get, they only pick the newest one. So how would you kind of solve this problem? Or how would you, like, you don't even have to use like this approach. Like how in general do you think the problem could be solved of this continuously updating database? Like high level. Okay. This might be a bit too technical, maybe. So yeah, I mean, it is a problem, and if you have a continuously updating database, you will have to do some overhead. But I would basically invest the time into doing that, but have it in like different granularities maybe. So like once an hour, you basically don't create new clusters, but you just assign each embedding to a cluster, and you store it in a new contiguous space in the SSD. So this way you don't have to touch all of the other blocks and all of the already existing stuff, but you just create basically a new database, but we're just linked to the old one with the same clusters. And then once at the end of the day, you can kind of create these new clusters to kind of split up the processing. Yeah. Yeah, another thing is like if a database bad across multiple SSDs, there I think the problem is not that big. But yeah, do any of you have any ideas? what you would do then. So now you don't have just vector embeddings which fit into one SSD, but they span across multiple ones. Do you have to stop? Or... The solutions are not that crazy, I feel like, that which I proposed. I mean, yeah. Or who has a... yeah.
Hello, yeah. Well, I would suppose like just do the computation on each of the SSDs and then compare them like using distributors. Like
yeah, okay. Yeah, I would probably do the same. Yeah. This was it. Takeaways. What should you kind of like take away from this talk? First, if you actually are interested in improving a RAG pipeline, they found binary quantization and then Retrieval algorithm. They offer good recall. And if you want to implement it on in-storage processing, they kind of showed that this is the approach to go. So on the pure technical way, I think this is a good takeaway. Then, for instance, in general, ISP processing design, what I kind of took away the most was their kind of mapping their stuff to the existing elements. And they kind of motivated me to see, okay, how many of the computing elements are actually already capable, not just to do some processing, but really competitive processing for real world problems. And yeah, you don't have to recreate the architecture. And lastly, the database layout to kind of avoid this error correction that they use the single level cells, which I think is like a big thing they did, to have like separate regions of SSD, one with more accuracy and one with more density, and also the way it allowed them to avoid the address translation. Yeah, that's it. Any questions? Other than that, yeah.
I think the SLC approach is pretty creative, but if they lose about like 4x the density, I think, of the memory, like do they do like an, I don't know, like an evaluation, like the cost that it might incur for each retrieval? Because now you lose like a fourth of your, right?
Yeah. You're completely correct. So they basically lose 3 times the storage density, but maybe they didn't do a direct comparison, which could be another weakness. But I think it's still worth it to do this SLC approach because it's only a factor of 3. And otherwise, I'm sorry, I have to go back all the way. Otherwise, normally the flash drive reads the embeddings, but then the error correction is done by the embedded processor. So now if you don't use this SLC with high accuracy, you cannot calculate the distance here anymore reliably, really, because you would have to send back the whole embedding. And then the embedded processors do the error correction, distance calculation, and the quick select. So you basically just use the embedded processors there. So I guess 3 times more storage density for like 12 times more performance is the trade-off. But they should have done a concrete comparison between them. I agree. Yeah. Other questions? Oh. Yeah.
Do you have some final remark? Okay, maybe you can also.
No, we're going to take a quick break. I'm saying some final remarks.
Okay, so my final remark is like Lionel mentioned, so there are a lot of heterogeneous components if you consider the storage subsystem, which are capable of doing a lot of computation. So I think we have a lot of scope to use, accelerate different applications, not only RAG or LLM, but other applications to map computations and then try to accelerate them within the storage, because most of your data is in the storage system typically. So that's one thing. Just one comment on the previous, on the discussion about reconfigurable parts of the SSD. So we have systems like smart SSDs, which have an FPGA within the SSD to perform different computations. But again, there are different challenges to that, but it could also be something that we can kind of explore more or look at how we can improve those kind of designs. That's my comment.
Yeah, so I mentioned this kind of reconfigurable hardware as well, because in the flash dies, you don't really have a processor, but you have these processing elements which exist. So kind of rerouting them for different applications, which I didn't explain before, but I agree. It's nice. Good idea.
Thanks, Rakesh. I will also add excellent talk. Weaknesses and discussions are well done. Thank you. I would also just challenge this RAG specific a little bit. So essentially in REIS, do we, or do they, I can't say do we because it's Safari paper, basically do it change the hardware, to support that. So when you say that it's RAG specific, I mean, it's a good thing to be specific because you can optimize the performance, but it can be also a bad thing because you're specific to one application. But here, do we really change the hardware for that?
Hello? You don't really change the hardware processing elements, so the processing elements stay the same, but to have kind of allow the system to be actually implemented in a real system, you would have to implement new instruction sets, which are also explained in the paper. So, and which would need cooperation with the SSD developers, which is fine if we see that, okay, RAG is like the super use thing and it needs the specific optimization and like these specific instructions. But I will grant, like, yeah, it's applicable to all of these general vector specific applications. So yeah, I guess I did the other discussion point before I then realized, okay, we can do more stuff with it as well. But yeah, I think I was just thinking, okay, wow, we have all of these computing units which can do all of this interesting stuff. For example, vector similarity storage. Are there any other stuff we can do with the processing elements in a storage, not vector comparison storage? And I'm thinking, okay, like, for example, nowadays RAG is not maybe as important as it used to be like a few years before, but I'm just imagining kind of this world where like any user or like company can like, okay, we have this problem. Some programmers, please program the SSD to kind of accelerate this task and reroute some hardware and to have this kind of on-the-go adaptation with the real-world algorithms as well. But I agree with you that it's not super RAG specific because we have the vector elements and it's only instructions. It's not actual processing hardware which gets changed.
That's true. And also there are prior works on proposing general purpose ISP framework like BlueDBM. So what I would suggest, maybe if you have time, maybe we can update your discussion slides by adding some references from prior work, because on all these topics actually there are prior works.
Okay, I need to read more on the prior work. I see already.
If you have time, would be nice.
Yeah, it's really interesting actually. If there's prior work, yeah, I'll update the slides.
Okay,
thank you for the feedback.
Let's thank the speaker again. Maybe we can take a short break, like 5 minutes, and then we will continue with the next present.